morning everyone and welcome to Chemistry Department IIT Delhi. And it's the 9th lecture in this series, and thanks to Shomik and his team for organizing these Sci-Tech Spins. Okay. And what I believe, what I hope, is that you get to learn something, whatever it is, from today's lecture. The topic that I have selected is, how do we detect light, right? And I'm sure you guys, all of you are in 11th and 12th standards, right? And some of you had exposure to biological courses, and you know the structure of the eye. So you have all these various layers over here which allow the light to enter, and then it falls on the retina. And over there you have some cells which you know as cone cells, rod cells. So if I'm thinking of color, and the human eye is sensitive to the visual, and you already know that there is a wavelength of these various colors that is associated with them. And typically, the wavelength that a human eye can perceive, if you read textbooks, they will say 400 to 700 nanometers. Okay, 400 happens to be the violet edge. Wavelengths below than 400, ultraviolet. 700 happens to be the red edge, but believe me, that I have these specs, I cannot see beyond 660. I have a spectrometer, I keep tuning the wavelengths and try to see. But some of the younger people I have seen, they can easily see 680, 690 nanometers. So our eye is limited over there. So all of these things, light when falls into the eye, it goes to the rods and cones are the ones that are responsible for color. Okay, and this, there are short cone cells, medium cone cells, and long cone cells, and they're named or they're designed so as to detect short wavelengths, medium short is blue wavelengths, medium is green wavelengths, and red color with the long cone cells. What is most important over here is what exactly is there in these cone cells that allows us to interpret the images or light that is falling. And there are these proteins called opsins. And these opsins are the ones that are responsible. There are 9 kinds of opsins, but not all are responsible for vision. Some of them are responsible for other activities too. But these opsins, they have some chromophores. Chromo is color. And these chromophores are the ones that essentially pick up or detect the incoming colored light, the color of light. The molecule that is responsible for this. And let me draw the structure. It's an important one to understand how we mimic these molecules, how we design some materials for that. So you have an aldehyde over here. This is called the 11 cis retinal. which can be replenished if you eat lots of vitamin A. Carrots. Now, why this molecule is important? The most important part over here, if you look at this, are these double bonds. The double bonds over here, they are conjugated. What do you mean by conjugated? Right, one after the other. I'm not sure if you've learned bonding, pi-orbital bonding. Yes?
Yes.
So if you look at the p orbitals, let's think of the z direction as pointing out of the board. And if I look at these p orbitals, the pz orbitals which are involved in the pi bonding, then all of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and to some extent this one also, you cannot say that this pz makes this double bond. I could also shift by arrows these double bonds, right? So these two pz orbitals could also make the double bond. That's what the conjugation is all about. What's important over there is that the electrons in these pz orbitals, you have electrons, right? And the electrons in these pz orbitals are not localized over here. They could be here, they could be here. They could be here. So it's kind of a box. This is kind of a box with some given length over here. All right. And because of this length, your electrons are moving freely, because all these pz orbitals are kind of talking to each other. So all these electrons are moving freely within this length of the box. There's a very simple model in quantum chemistry, and that's called the particle in a one-dimensional box. I'm almost certain you've not studied this in school right now, and will not do it. What you should know from the particle in the one-dimensional box model, and that is the first thing that you will ever study when you study quantum chemistry or quantum physics, is that the energies, and this is something that you know, the energy levels are quantized. Okay. This is something you've seen in the case of the hydrogen atoms, the Bohr model also, right? So when you do that, but over here what you see is that the energy depends inversely on the length of the box, the square of the length. This L is the length, H is your Planck's constant, N is an integer, 1, 2, 3, 4. Mass is the mass of the particle that is in the box, the electrons over here. So if I were to draw these energy levels, I would have, n square would be, well, these are constants for a given box. So n square would be 1, 4, 9, 16, somewhere. Okay. Now the most important thing is that all these energy levels, I would start filling these pz electrons into them, right? And up to a certain point, they would be filled. I don't know which energy level, how many electrons are there. I'm not doing all that counting. Depending on the length of the chain, I have. But let's say this is my level, and then we also know that one electronic level can have only 2 electrons. So I could have something like this. Let's say this is my highest occupied level. Now what it gives me is a gap. corresponds to the energy of the incoming radiation, incoming light. And energy is nothing but h nu is frequency or c by lambda, so related to the wavelength. So if this corresponds to the energy of the incoming radiation, then one of these electrons could be excited over here, right? Now what does this opsin do? Right? Opsin is taking the light in. One of the electrons in these chromophores is getting excited over here. Okay. And from your biological courses, you also learn that this is converted into an electrical signal taken up by the synapses back to the brain, where some computer scientists would say that there is a lot of artificial intelligence at play, reconstructing, and well, all of that comes from the human body, the concept of artificial intelligence and machine learning. What do we do? Right? As we grow up, we keep learning things. So that's what the brain also does, actually, reconstructs that. So once you have these electrons and they are separated, all you need to do is to take out these electrons. And you know, all these opsins, they have very complicated structures. In between you have these, so there are pockets over there. There are pieces of molecules, so as to say, which can pick up this electron and send it over. There's also another way that it's not always the electron that is being picked up, but once you remove an electron from here and take it up there, there's also an empty space that has been created over there. One electron can also go there. In the language of semiconductor physics, it's called a hole. So it's not just that the electron can go out. The other way, the electron can come in also. So both ways you can transmit your electrical signals. Now the thing is that our eye, as I said, is sensitive to 400 to 700 nanometers. But there are loads and loads of applications outside this regime. It's very convenient because we can see 400 to 700. But yeah, show me this remote, please. Can you see anything? Ah, ma'am, there, you're really good at this one. See it from your eyes, not from the camera. Can you see something?
Yes.
Can you?
It's white, slightly. Not now. But
Can you see any light coming out of this?
no, not red.
Now see it with your camera.
Yeah.
Yeah? So all of you can try this experiment at home. Pick up your TV remote. And put it in front of your cell phone camera, and you'll see a faint pinkish glow. Okay. What exactly is happening? Yeah, sure. Yes, this is infrared. All of these are infrared. And why we detect them in our camera is because all of these electronics that you have over there are made up of silicon. Silicon has a band gap of 1.1 electron volt. So this is the gap, right? And I could convert that 1.1 electron volts, I get about 1100 nanometers. Anything which has energy more than 1100 nanometers would be detected by silicon. Well, practically it's not 1100, it comes to about 900, 950 nanometers. And these are typically, I think, 850 nanometers, the commercial available ones. These are very cheap infrared things which the TV has the same sensor, and they are all built on silicon. So what you're going to do over here, if you have to mimic the eye, and you want to go beyond that also, right? You want to have infrared vision. A lot of applications, right? A lot of medical applications, a lot of defense applications, a lot of space applications. I cannot give you an exhaustive list over here. So you need infrared. So how do you make these devices? How do you fabricate these devices? How do you design these devices? Okay. Now, if I have to design a device, I understand that I need this gap, which can be excited by some wavelength. And you can use a lot of molecules. Of course, the first thing that should come to any of you is, let me change the length of this molecule. Let me make it longer. I'll have smaller energy gap. Let me make it shorter. I'll have larger energy. There's another class of very interesting materials that are available to us. As I already told you, silicon. Silicon happens to be a semiconductor. Right? And everybody understands what a semiconductor is. I don't need to tell that. So, there are loads and loads of semiconductors. And their band gaps can vary from far infrared to even in the ultraviolet region, which is actually called the vacuum ultraviolet region. Because air molecules like nitrogen and oxygen absorb below 180 nanometers. So you need vacuum in order to do anything over there. You're not from the generation who's seen vacuum tubes. Our televisions used to be this thick with a lot of vacuum tubes, and that's where the vacuum ultraviolet was generated. Okay. Anyway, so we are not generating, we are here to detect things. Okay. So these semiconductors, yeah. If you have any questions or anything, please do shout out. I heard something. No? Alright. So we have these semiconductors, and all these semiconductors have their defined gaps. But nature has already made some mechanism so as to collect that electron that was excited. Okay, so if you go on, we need to worry about that as well. How would I collect that particular electron? Or how would I pump in another electron so that this can be taken out, and once it's taken out, I'll have my electrical detection mechanism at play. So the most important thing over here is to design this. Alright, so let me think it loud. I need my material, my semiconductor material. Let me make a block diagram over here. So this is my semiconductor. Okay. And the semiconductor has some gap. I want to take the electrons up there, but once it's excited, it doesn't have any directionality to go. Right? Why? It doesn't, it's free to choose anywhere to go, it can go. So if I have two electrodes over here, it can go anywhere, either up or down. And if it goes both ways, I'll never see any current. Because whatever the number of electrons that go up and the number of electrons that go down become equal. It's zero. So I need to bias it. minimize it by putting something which I will call as the electron transport layer, ETL for short. And then you work the design of this, don't worry. Then I want the electron to come in from here, or the hole to go out from here, right? So no marks for guessing what this should be called. The whole transport layer. And once that is done, I have my bias that I have already provided. Okay. Then I can just deposit some metal contacts and be done with it. Okay. Yes. So light should fall on this semiconductor, electrons move up, the holes move down, and then I will take them out and connect it to an ammeter to measure the balance. Right? So you can name loads and loads of semiconductors over here. You can start with, we have a period. So you look at the periodic table and you want to design something. You see, okay, let's take silicon. Silicon is something which has a 1.1 eV, electron volts is the unit of energy. You can multiply it by the Avogadro number to get into joules. Electron volt is much more used in this community. So 1.1 electron volts, silicon, and then I want to go close to silicon. So if you remember, silicon happens to be below carbon, and I go a bit left and go a bit right. Right. So I will go to group 3. So then carbon was group 4. So if I have to maintain my neutrality, then I need another element from group 5. So these are called 3,5 semiconductors. So I can have aluminium nitride, boron nitride, gallium nitride, okay. So I can have aluminium, boron, gallium, nitrogen, phosphorus, arsenic. Just make a combination of them. Not just make a combination, you can even make alloys of them. So for example, you can have indium gallium nitride. It's a very important one. It's because of this that you see all these lovely displays today. Led to the Nobel Prize, the indium gallium nitride, or gallium nitride you can say, is the blue emitting light LED. Okay. And without blue, you could not have the entire spectrum of visible colors. Red and green are much easier to make. So blue LED was gallium nitride, or indium gallium nitride to be exact. Then you can even move further apart in the periodic table. I'm using this convention of 3,5, and your chemistry teachers would actually kill me for that. It should be called 13, 15. Okay. Old school, sorry. Move away, move one block here and one block there. You will get 2 6s. Okay. Cadmium, zinc, mercury, sulfur, selenium, oxygen. But you need to choose your materials so that you can access whichever region of the electromagnetic spectrum you're interested in. Now, gallium nitride, I already told you, was something in the blue ultraviolet. You could go on to indium arsenide or gallium arsenide that happens to be in the infrared. You could, just choose one. And actually, I should give you some examples. Gallium nitride, ultraviolet. Indium arsenide, infrared. Lead sulfide, even more infrared. Okay. The wavelength corresponds to roughly about 3,000 nanometers. Lead selenide, you shift even further in the infrared. Lead telluride, even further. So what's happening? There's got to be some logic behind all this. You just can't pick up a material and say, okay, let's see what the wavelengths are. And there's a deal of logic. A very rule of thumb, if it's more ionic, okay, then it's got to be a larger band. If it's more covalent, the band gap will be rather small. Okay. It will work most of the time, there will be exceptions. As you've seen, chemistry is the subject of exceptions, right? So you can choose your materials over there. All right. Now, okay, still have some space. I have my semiconductor whose gap, let me make something like this. And this gap corresponds to the wavelength of light that I wish to be taken. Now I said, the moment I shine light onto this, one of these electrons goes here, one remains there. There's a very, very rough picture that I'm making. Actually, when you talk of semiconductors, it's not just one single energy level, but then it's a band. Okay, so, but we can live with this because the concepts will not change. Now, I want this electron to go over to the electron transport layer. Things can move only if they're all lazy things, just like you and me. Always want to go down to a lower energy. This fellow is also lazy, wants to go to a lower. Well, actually, if you're looking at holes and the movement of holes, then that's, so this is photons. That's a lower energy level for the photon. If you want, you can think of the electron moving from here to here. But I don't know what you like to think. Thinking about the hole is much easier. Because if you think of a bubble in a bucket of water, what do you want to say? The bubble moves up or the water moves up? So, I have my the EPL here, this semiconductor here, and the whole transport here. And then the metallic contacts follow. Now these are things where you can just pick up your semiconductors, make these contacts, and be done with it. But do I have some more time shown? Okay. Then let me give you a flavor of some research over here. Now you know how to make devices, and we, in a short while, we'll see how these devices are made with some of the steps that we do. But now, you want that devices are more efficient and perhaps can do a few more things than you desire. So you want them to be more efficient, and you'll say, okay, this is my device, okay, before I go into that, once this fellow goes up, this doesn't stay here forever. It has a lifetime. And these lifetimes could be on the order of nanoseconds to milliseconds to microseconds, depending on what your material is. So I have to capture the electron and hole before it collapses down. It could recombine, it could get distributed somewhere. Okay. It could get lost. Essentially, I don't want it to do this. So I want to design some materials where I can ensure that it doesn't get lost. Now I'm looking at the band gaps of all these materials, and what I've not told you is that all these band gaps, and come back to the hydrogen atom, the n is equal to 1, the ground state. You all know the energy is minus 13.6 electron volts. It is with respect to when the electron and proton are very, very far. That is when I say it is the zero of energy. So they are free particles. They do not feel any Coulomb attraction between them. So I define a zero of energy. And with respect to that, I define all my energy levels. So whenever I am defining these energy levels, I never mentioned about the zero of energy, so let me get that in. Let's say we have this zero of energy somewhere over here. And so let's say, okay, the retinal doesn't have to do anything, this is zero, but now I bring in another material. Another material whose band gap is perhaps similar to this, but shifted. Okay. And this is possible to make. I already told you about indium gallium nitride, that was an alloy. But what one can do. So you think of a solid material. It has a crystal structure. Think of sodium chloride, easiest. Okay. Everybody knows the crystal structure of sodium chloride. I could take another one. Right? Sodium chloride happens to crystallize in the face-centered cubic structure. I could take another one, potassium chloride, which also crystallizes in the same structure. And I take a crystal of sodium chloride and I start throwing on top of it potassium chloride. Potassium would have a slightly larger lattice than sodium. It's a larger cation, so it will have a larger lattice constant. So there will be some strain over there. So if I try to make layers and layers of potassium chloride, it would like to go into its own structure. Cell would be this big, sodium chloride would be this small. There will be strain at the interface. It can get broken. But on the other hand, if you can choose two materials which have hardly any strain, and the typical values that the physicists give is about 4 to 5% is the limit. Then we can grow one on top of each other, which is known as epitaxial growth. One on top of each other. So if you can do that, and you can find the materials which have the correct energy levels, then you can make such kind of a heterostructure. Materials, heterostructure. The moment you make this heterostructured material, you ensure that after excitation with light, the electron would immediately be found here, and the hole, because this is a lower energy for the hole, even if it was there, it would be always here. You have a natural charge separation. Right? At the moment you have your natural charge separation, now I can put my EPL over here and the HTL over here. There are various materials for EPL and HTL. Okay, for example, again that would depend on what is the energy of these EPLs and HTL with respect to the other semiconductors that you work with. The energies are always referenced from vacuum or zero. So this is what my research goes into, to design some new heterostructured materials. Okay. With that, I think I can stop. And if you have any questions on this, I'll be happy to answer. And we have Dr. Rajeshri over here, standing. She's ready to take you to the lab to show you how these devices are fabricated. But before that, do you have any questions? Yes, please. Right, absolutely. Yes, please.
How exactly do you use like the potassium chloride on top of the solution? Like how do you use that to detect which matches metals?
Okay, sorry. That was just a very generic example that I gave you because you're familiar with sodium chloride. Actually, nobody makes sodium and potassium chloride for that matter. What you could make is, for example, indium arsenide on top of gallium arsenide, or indium gallium arsenide on top of gallium arsenide, which is how to make it is what you ask. There are very variety of techniques over there. One thing is, which is very, very expensive also, is called molecular beam epitaxial. So you have a molecule of these materials, it comes and it's all done in ultra high vacuum conditions. Okay. Those of you who visit Sonipat, I could show you one of these instruments. It's a huge thing, it occupies this entire room almost. But you have a substrate. On top of that substrate, you put a molecular, so molecules of these. So if you put gallium, arsenic, you put the precursors of these, let them react at whatever desired temperatures, they go and stick to this substrate. The substrate, of course, if it's gallium arsenide, I can throw indium gallium arsenide on top of it because that would have a very small lattice mismatch. There are other methods. For example, one is called atomic layer deposition. So you put one layer of atoms. So if you think of a crystal, you can think of layers of atoms, right? Exactly like that, you put layers of atom and let them react. We, on the other hand, use some chemistry approaches which are similar. So, you see, I have a material and think of a crystal. The face of the crystal, if you look at it, it is going to have both cations and anions. Let me throw in, since we are chemists, we work with solutions. So I take a solution, let me throw in some anions in this solution. These anions are going to go and get attached to the cations. Now I'll have a surface which will be very rich with anions. Right? Okay. I precipitate these fellows out, clean them so that I don't have any extra anions in the solution. I redisperse them. I put some cations now. These cations will now form an extra layer. Okay. And I can do this process repeatedly to form these layer by layer assemblies. This is actually known as the colloidal atomic layer deposition. Okay. There are variety of other techniques, but all the semiconductor industry in fact uses the physical machines, not the chemical ones.
Is it similar to crystallization?
To some extent, yes, but not exactly. Not exactly. Crystallization is more spontaneous. Here I'm forcing these things to come on top. Thermodynamically, of course, this is also spontaneous. It's not, yeah.